Okay, today we're going to look at binomial distribution. We're not going to get too deep into this because to really appreciate the binomial distribution, you need either a computer program or a table, and you don't want to get computers involved any more than we have to. And I don't have the table in the text, so we won't go into that depth. If you are interested in further depth, you can always look up the information online. Or perhaps if you're really curious, take a statistics course. So we're going to talk about binomial experiments and get some basics down. We're talking about multi-stage experiments that satisfy some pretty specific criteria. Before we go on to analysis, we need to introduce and explain the criteria so that we can recognize experiments that fall into this category. Experiments that satisfy each of these criteria are called binomial experiments. A binomial experiment is an experiment with a fixed number of repeated independent binomial trials where each trial has the same probability of success. By a binomial trial, we're talking about there are two possible outcomes, success or failure. Our first criterion involves the subject or the structure of the stages. Each stage of the experiment should be a replication of every other stage. We call these replications trials. An example of this is flipping a coin 10 times. Each of the 10 flips is a trial, and they all occur under the same conditions as every other. Further, each trial must have only two possible outcomes. Those two outcomes are typically labeled success and failure. Even if there is not a positive or negative connotation associated with these outcomes, experiments with more than two outcomes in their sample space are sometimes reconsidered in a way that forces you just two outcomes. All we need to do is completely divide the sample space into two parts that we can label success and failure. For example, your grade on an exam might be recorded as an A, B, C, D, or F. But we could instead think of grades A, B, C, and D as success and grade of F as failure. Trials with only two outcomes are called binomial trials. The word binomial derives from Latin and Greek roots that mean two parts. Independent trials. The next criterion that we'll be looking at for is independence of trials. We said that two stages of an experiment are independent if the outcome of one stage doesn't affect the other stage. Independence is necessary for the experiments we want to analyze in this section. Next, we have a fixed number of trials. We require that the number of trials in the experiment be decided before the experiment begins. For example, we might say flip a coin 10 times. The number of trials there is fixed at 10. However, if we say flip a coin until you get 5 heads, then the number of trials could be as low as 5, but theoretically could be 50 or 100 or more. We can't apply the tools from this section in cases where the number of trials is indeterminate. Next, we have constant probability. The next criterion needed for binomial experiments is related to the independence of the trials. We must make sure that the probability of success in each trial is the same as the probability of success in every other trial. Now let's look at some examples here and determine, are these experiments binomial? We draw a card from a well-shuffled deck, note its suit, and replace it. Repeat the process 5 times. This is a binomial experiment. What are our possible outcomes? We haven't defined what success or failure would be. So our possible outcomes are getting one of the 52 cards. So not binomial. Draw 5 cards from a well-shuffled deck and count the number of clubs. Again, we do have a set number of trials, so to speak, but again, What is success? What is failure? Now, if we change this and said getting a club is considered success, we could look at it. And right now, not binomial. Draw a card from a well-shuffled deck. Note whether it is a club or not and replace it. Repeat this process 5 times. So we have two choices. It is a club or it is not a club. We're putting the card back in the deck, so the probability of getting a club will always be the same. 13 out of 52 or 1/4. So this is binomial. Draw cards from a well-shuffled deck until you get a club. Indeterminate number of draws, so indeterminate number of trials, so not binomial. So we have a binomial formula. If we flip a coin 100 times, you might expect the number of heads to be around 50. But you probably wouldn't be surprised if the actual number of heads was 47 or 52. What is the probability that the number of heads is exactly 50? Or falls between 45 and 55? It seems unlikely that we could get more than 70 heads. Exactly how unlikely is that? Each of these questions is a question about the number of successes in a binomial experiment. Flip a coin 100 times. Success is flipping heads. We could theoretically use the techniques we've seen in earlier sections to answer each of these, but the number of calculations we'd have to do is astronomical. Just building a tree diagram that represents this situation is more than we could complete in a lifetime. It would have put the number in perspective. If we draw 1,000 dots every second and we started at the moment of the Big Bang, we'd currently be about 0.000000003% of the way to drawing out those final nodes. Luckily, there's a shortcut called the binomial formula that allows us to get around doing all those calculations. So our binomial formula states, suppose we have a binomial experiment with n trials and the probability of success in each trial is p. Then the probability that the number of successes is A is equal to NCA, combinations, n things taken A at a time, times P to the A power times 1 minus P to the n minus A power. 1 minus P being the complement of P. We can use this formula to answer one of our questions about 100 coin flips. What is the probability of flipping exactly 50 heads in this case? In this case, n is 100, p is 1/2, and a equals 50. So p, the probability we flip 50 heads is 100 C50 times 1/2 to the 50 times 1 minus 1/2 to the 50. Unfortunately, many calculators will balk at this calculation. That first factor is an enormous number, and the other two factors are very close to 0. Even if your calculator can handle numbers that large or small, the arithmetic can create serious errors in rounding, which is why we typically use a table. However, we can do this for smaller numbers. So compute the probabilities rounded to 3 decimal places in the following events related to rolling a standard 4-sided die with faces labeled 1, 2, 3, and 4. And so what is the probability of getting 4 2s? So in this case, n equals 10, a equals 4, p equals 1/4, or 0.25. So our formula is 10C2 times 0.25 to the fourth times 0.75 to the sixth, 10 minus 4. And we get 10, choose 2, or 4 is 10 factorial over 10 minus 4 factorial, 4 factorial, which is 10 times 9 times 8 times 7 times 6 factorial over 6 factorial times 4 times 3 times 2 times 1, which is 210. I have 210 times 0.25 to the fourth times 0.75 to the sixth, and this gives me to 3 decimal places 0.146. Okay, so now we're going to look at 20 times. So now I'm looking at n equals 20, a equals 4. So I have 20C4 is 20 factorial over 20 minus 4 factorial, 4 factorial. It's 20 times 19 times 18 times 17 times 16 factorial over 16 factorial times 4 times 3 times 2 times 1. And that gives me 4,845. So probability of rolling 4 twos is 4845 times 0.25 times 4 times 0.75 times 16, which gives me 0.190. And lastly, we're looking at 30 times. N equals 30, A equals 4. We have 30 CA, or 4. 30 factorial over 26 factorial, 4 factorial, which gives me 27,405. So probability of rolling 4 twos here is 27,405 times 0.25 to the fourth times 0.75 to the 26th, and 0.060. And that is the extent of what we will be doing, but I do want to talk a little bit about how this works further. And should you go into statistics, you will definitely dive into deeper details with the binomial distribution. So if we're interested in a probability of more than just a single outcome in a binomial experiment, it's helpful to think of the binomial formula as a function whose input is the number of successes and whose output is the probability of observing that many successes. Generally, for a small number of trials, we'll give that function in table form with complete list of the possible outcomes in one column and the probability in the other. For example, suppose Christian is practicing her basketball free throws. Assume Kristen always makes 82% of those shots. If she attempts 5 free throws, then the binomial formula gives us these probabilities. Using the formula, we would get these probabilities here. 1, 2, 3, 4, and 5. A table that lists all possible outcomes of an experiment along with the probabilities of those outcomes is an example of a probability density function, a PDF, not the file type. PDF may also be a formula that you can use to find the probability of any outcome of any experiment. If we want to know the probability of a range of outcomes, we could add up the corresponding probabilities. Going back to Kristen's free throws, We can find the probability that she makes 3 or fewer of her 5 attempts by adding up the probabilities associated with corresponding outcomes. In this case, 0, 1, 2, or 3, which we've done here. The probability of an outcome of an experiment is less than or equal to a given number. It's called a cumulative probability. A table of the cumulative probabilities of all possible outcomes in an experiment is an example of a cumulative distribution function, or CDF. CDF may also be a formula that you can use to find those cumulative probabilities. Keep in mind, cumulative probabilities are always associated with events that are defined using less than or equal to. If other inequalities are used to define the event, we must restate the definition so that it uses the correct inequality. Here are the PDF and CDF for Kristen's free throws. Now, should you go into statistics or just look at a statistics book, you can find a huge table that lists this. Also, I want to say it's Google Docs or Google Sheets has programming embedding that will do this for you. Since on an exam for in-class students, you wouldn't be able to use that computer. I'm just not going to go into depth on this. So this will end the binomial distribution section.